had enough coffee now to re-energize. Lots of good questions at the end of each of the talks. Our first speaker in this part of the session will be Ellis Yuan from the Institute for Advanced Study. We'll talk about some geometric aspects of Feynman parametrization.
Hello. Okay, good afternoon, everyone. First, let me thank the organizers to invite me to talk in this great conference. I have to apologize that while I put the title here as some geometric aspect of Feynman parametrization, actually this is a work in progress with Nima Kamikamit, and there are still many things to be understood, and the contents that we'll cover in this talk are mostly not really about physical amplitudes, but about a class of objects simpler but mimics the structure which we understood very well. And I hope that will ultimately give us some intuition on how to deal with the actual amplitudes. So our general purpose here is to understand better the general structure of the singularity, have a better understanding of the singularity structure of Feynman integrals that people encounter in studying the scaling amplitudes. And so, in general, the study of scaling amplitude falls into two things. One is to study the integrand, another to study the integral. Over the years that developed, although there are many connections between the two, but the developments are largely going on independently, and we already have a very nice and rich understanding of the features of the integrand, and there are many analogs of the questions and the studies between the two sides. For example, both of them can be decomposed. We are studying from summing over the Feynman diagrams that we read from the Lagrangian, and the result can also be interpreted as expressed in terms of some other objects. And we can study the singularity structures on both sides. They are of relatively different quality. Especially on the integrand side, we now have a better control of the singularity structures that we encountered, at least in some very nice series. And we also have a certain recursion relations, and it turns out that these recursion relations themselves also have a very pretty geometric interpretation. And now, ultimately, it emerges into a picture called amplitude in n equals 4 super Young-Mills, where we have a single object describing the amplitude that we encounter in this theory. However, in comparison, on the integral side, although people have spent tremendous efforts in trying to collect data and understanding structures here, the understanding on this side is still not so well developed as compared to the integrand side. And for some recent developments, I refer to these references here, and of course there are many more. For this talk, what I'm going to look at is the branch point and branch cut, and in general discontinuity structures and the symbols of that might arise in a given integral. And it may also be interesting to get a better understanding of how the two sides are related. And in the end, we hope that there could be also some kind of unified understanding of the whole structures about the integrals here that mimics what we already have, at least for specific theories on the integrand side. When we look back into history, it appears that the closest point to this hope is the Feynman parametrization, because this is something very general. We can write it down for any Feynman diagrams we are given with, and the structure is also very unified. After translating into the Feynman parametrization, we have a single denominator and the structure here is also very well understood. In this notation, I'm using the Z to genetically denote the whatever kinematics data entering in the scanner. The point here is that this is not just a computational method that is convenient. People are actually also using this representation to try to directly understand the singularity structures of the integral. And this already dates back in the 70s. For example, if you look at this famous book. And the general method used in such analysis is the so-called lambda equations. And Anastasia also talked about it last week. Yes. So in general, these equations can be summarized as follows. After we get this representation, then the equation is that this d has to be equal to 0, together with a bunch of other equations for each I. The I denotes the specified different alpha parameters. Either the alpha I have to be 0 or the derivative of d with respect to alpha I has to be 0. So what this equation does, roughly speaking, this equation describes the condition for pinching singularities of the integrand. For example, here I use these red lines to denote the integration counter, and the blue dot denotes the singularity of the integrand. And then the equation just describes basically when these different singular points pinch. When it pinches, the counter cannot be deformed, and generically it means that we have to have singularity developed in the integral, and that's basically the solution for the external data that specify these locations. Now here, let me quickly review some features of this analysis. First of all, for the lambda singularities, which means the solutions to the lambda equations, are naturally classified according to how many alpha parameters are there, and they have a nice graphical interpretation relation connected to the so-called the degenerate graphs. And also, for each solution, we can try to understand what kind of singularities does this solution correspond to. Are they poles or are they branch point? And in the case of branch point, what types, or also whether these kind of solutions are actually in a singularity or not. Also, in some simple cases, once we know there's a branch point and we go across a branch cut that attached to it, we can try to understand, try to work out what the discontinuity when we go across this cut. For example, in the simple integral which gives a log, the calculation basically means that the picture is roughly like when we deform the data to go across a cut, this singularity of the integrand once around one of the end deform the counter, but the counter has to be connected to the original value. The counter has to be deformed backwards. And in doing this, we pick up residue around the singularity of the integrand, and this basically tells us, gives us the information of the branch cut. However, beyond this simple case, in general, to obtain the information about the discontinuity in this way is quite complicated, as you can imagine. There are some inconvenience about this analysis. First of all, the lambda equations are just necessary conditions for the singularity. They are not efficient. And the basic reason, as I understand, is that it tells you when the pole pinches. It doesn't really necessarily tells you what the information about the details of the counter, unless in some specific situation. Also, when we want to work out more information about the nature of the singularity, we have to work locally in the neighborhood of the solutions to get more understanding of how the integral actually behaves, and that requires case-by-case study. So in the most generic situation, there's not great hope to understand the entire structure about the given integral in general. And so we can expect that the method can be complicated in general. Of course, we know that Feynman integrals themselves are very special functions, and so there should be some remarkable thing happening. But in practice, we still encounter some complication. And I think the main reason to this complication is also partly mentioned yesterday in Mark's talk. So just to get some sense of this, when we let's look at this generic one loop endpoint function, the scalar integral. Once we have the Feynman parametrization, although we have a single denominator, it's of a very high power. The geometric meaning attached to it is not quite clear, and also we have an n-fold integral. However, in general, we already know that the result can be well expressed in terms of just some of the dialogue functions, which are naturally twofold integrals. And so there's apparently a mismatch between the two. We know that in the end, this function has to be, we should be able to get this down to a twofold integral, as Jake also commented. But in practice, it's a little bit hard to see how it goes. But that's the main point. If we want to get a better understanding of the similarity structure about the integral, it might be helpful to really get down to this level and then try to use some methods like the Landau equations to get extract more information about the structure. And also related comment here is that this is never in most cases, this is not the way how we actually compute this integral. Instead, we decompose it into boxes at first. And this is my comment previously. However, in this talk, I'm not going to discuss how to get down to the desired level of integrals in general. What I'm going to explain, to show you in this talk, is that once we have this kind of representation, what we might gain from this fact. It turns out that there's a very nice story, at least in a class of integrals that I'm going to show you. But to reach the object that I'm going to discuss, let's first look back at a simple example. This format box again. It's very simple. We can try to design some clever parametrization for the kinematics, like this. And once we have the Feynman integral, we can try to make a choice of the delta constraint and then directly integrate two variables away. It's quite straightforward. And then in some choice, we land on such a representation. We can make this thing nicer by adding a small factor in the numerator in order to make the integral itself to have unit similarity. And then we can turn this into this expression. The nice thing about this is that this has a natural interpretation in terms of an integral in CP2, which is a projected space integral. And the nice thing here is that this integral is uniquely determined by the two curves that we specify within the Q and L, one line and one quadric. So this is a very special integral that is totally fixed by the geometry that we specify. And since it is totally determined by geometry, there might be some hope that the singularity structure can also be very well described just by geometry directly. And that's what I'm aiming for. But before attacking this problem, I'm going to look for a class of objects which is even simpler and even cleaner. Because here I'm still having the quadric curve, which is still a little bit complicated than the linear one. So why don't we use just linear curves? And so just to remind a little bit, the result is just a sum of dialogues which can alternatively be naturally defined in terms of the iterated integrals. And when we review the geometry related to this integral in the same way, we have a similitude for the case of the dialog, and the geometry related to it is nothing but two special triangles, one defining the integration region, basically defined by the equations of each of these components being 0, and then another small triangle specifying the integrand, meaning that the integrand has logarithmic singularities along each of these lines. So we get two triangles and they uniquely fix an integral which gives us the dialog. And this can be generalized into higher dimensions. So the object I'm going to look at, to seek for is the one that generalizes this kind of configuration. And we already have a prototype, which is a so-called all-mortal logarithms. So in general, it's defined like this. We start from, we first fix some specific dimensions, CPN, and then we define specify two simplices, which I here call M and L. So I left one to define the integral, in other words, this integral omega L is some top form that has logarithmic singularities on each of the boundaries. And then this M just specifies the integration region. And this pair of simplices define the general or multiple logarithms, which generalize the dialog that I showed you previously. Here I just quickly summarize some of the properties, well-known properties of this class of object. First of all, this integral it becomes singular once the two simplices share some common faces of the same dimensions. And it is 0 if one of them degenerates in the sense that its volume goes to 0. Also, we can try to apply a projective GL n+1 transformation simultaneously on the two simplices, and then after this, and under this action, the whole object has to be actually remains invariant. And moreover, importantly, this kind of integration has an additive nature with respect to both of the amplitude. For example, we can think about on either side, we can think about start with two simplices and try to glue them, and the resultant integral should not know anything about the gluing boundary, which is not the actual boundary of the whole object. And due to this additive nature, actually we can consider something more general. In general, we can think about a pair of generic polytopes in CPN and define similar integral. And this integral is also completely fixed by this pair of polytopes. And this is the object I'm going to think about. For these polytopes, you can either specify by their boundaries or specify by the convex core of their vertices. You can think in either way. And so this is a very nice class of Poier integrals that we can start with in the procedure of trying to understand geometrically the singularity structures of the integral. And the hope is that the lesson that we learn from here could help us get some intuition of how to understand better the Feynman integrals that we encounter. So how do we understand how is the analytic structure systematically encoded in the geometry for this class of integrals? Now let's first look at the discontinuities. And to make the story simple, let's focus on the dialog. And we know that it has a branch cut from 1 to infinity, depending on the d, whether this d locates on this interval or not. It either sits on the branch cut or not. And in the first case, it's below 1. It doesn't have a branch cut. In the second case, if we deform analytic continuity to some positive value bigger than 1, we are on a branch cut, and once we are across this cut, we should get something non-trivial. And it's very intuitive when we look at these two pictures, because on one side, there's no overlap between the boundary of one triangle with the other. But when there is a branch cut, when we are sitting on a branch cut, there's a non-trivial overlap between this line and the integration region. And so we can think about, we can imagine that the discontinuity across this branch cut has to be encoded locally on this boundary. And so we can do a test. We copy this boundary and copy the locations. And we now basically treat this curve, which is this intersection, as the new integration region, while this one synthesis defined by the two boundary points as our new integral and try to compute. And nicely, the result turns out to be exactly the discontinuity that we pick up by going across this point. And we can do this once more because we're still in dimension 1 and have a log function which again has a branch cut from minus infinity to 0. And the story is quite similar. It depends on whether the z sitting on which side of the 0. When we do similar computation, in other words, when we are in the situation of sitting on a cut, we can just project the integral. We can just focus on the intersection here, which is a zero-dimensional synthesis, and also restrict the integral to this case. And the result is just 1, and which up to a 2 pi I is just the discontinuity that we pick up. Of course, this branch cut is nowhere to be seen in the original dialogue, as can be easily seen from this original picture, because when the z locates here, the triangle again has no overlap with any of the integral boundaries. So this is very nice, and actually it can be immediately generalized. So the general prescription is that to determine whether we are sitting on a cut, we basically just look for the intersections of the hyperplanes defining the integral with the region with the integration region. And in general, it could happen that there are several lines intersecting the region, like in this case. And then what we do is that for each intersection, we restrict the integral to this hypersurface and regard the restricted geometry to give us the new integrand. And on the other hand, we take the intersection to be the new integration region. And then we compute another integral that depends on these two new polytopes arising from the above analysis, and we compute it. And in the case of the several intersections, we basically just sum them up. And this should give us the discontinuity that we pick up by going across the branch cut of the original integral. And as I pointed out previously, this procedure can be iterated for discontinuity of discontinuity, possibly after a proper analytic continuation, if necessary. And the basic reason is that after we do the restriction and pick up the intersection, the new picture is again a pair of polytopes in the lower dimension. So this is a general story about the discontinuity for this kind of integrals. Now let's go to the differentiation. We can also try to analyze the structure of the object by taking derivatives and see what's happening. And before this, let me remind you that there's a nice story happening to these two operations when we look at them in terms of the symbols. Once we get a list of symbols for a given function, the discontinuity acts only on the first entry, while the differentiation only acts on the last. For example, you can look in more detail in this nice paper by Trout. So this kind of picture suggests that there should be another nice story associated to taking differentiations, which are analogous to that of the discontinuity. And here, by taking differentiation I mean the differentiation with respect to the external data, but not the dummy variables that we integrate over. This should also be more powerful because this can potentially tell us the information, specific information about the entries, and also we don't have to worry too much about which kinematic region we are really sitting in. And as I mentioned before, there should be some kind of dual between these two geometric features. So here, first let me make a general conjecture. There's one conjecture that we have that for any integrand that we specify, an N form in CPN, which has unit singularities, then once we take derivative with respect to the external data entering its definition, then the result has to be a total derivative of some lower form, which is the N1 form in this case. This is something that we currently don't have a rigorous proof, but it works in many situations. For example, you can take this simple differential form defined by a triangle in CP2. And we can vary one of the vertices, and then the result is the total derivative of a one form, of this form. Now, of course, the solution to this lower form should not be unique. It's up to a closed form, but it doesn't matter because all we care about is the integral, and by the well-known Stokes' theorem, it's just related to an integral that restricts on the boundary. We might wonder whether this thing can, again, turns out to be some nice combination of the polylogarithms defined on the boundaries. It's not quite obvious from the start because this lower form that we get directly is not really some form nicely associated to a certain given geometry. We should only expect this to happen when we restrict it to the boundary, but not generically on the bulk, in the bulk. Yeah. So let's see. This is the structure that we should expect when we take derivatives. And as you can see in this simple example, when we take derivative, in general, we should expect that dialog has some function of our lower weight. And more generally, we can summarize in this form as a linear combination. And the question is, what should be the natural functions entering in the D log and also on the remaining part? And it turns out that indeed this latter part is again some polylogarithms, but of a lower transcendental weight. And as for the function entering here, there's actually a very nice geometric picture related to this latter part, as I'm going to show you. But here I'm not going to tell you the reason why this is so, but I'm just going to basically describe the result that we get. And to make the result more transparent, I also assume that the data defining the integrand is specified by the coordinates of these vertices. And when we take differentiation, we are varying these vertices. Now, here is the structure. Here I'm using this big object as some polytope for the integration region, and this small one, blue one, for the integrand. And once we want to get the result, about this differentiation, the procedure is like this. Every time we pick up a specific surface of the integration region together with the plane it defines, and we focus on the point with respect to which that we differentiate. And now we can project this polytope or the integrand through this point, and we get some projected new polytope that sits in this hyperplane. Now we can use this new projected polytope as a new polytope for our integrand, and this small face for our new integration region. And the factor here that I told you before is exactly the integral defined by this. Sorry, this is not quite like by these two new polytopes on this hyperplane. And for the entire result, we basically just need to sum over all the faces of one polytope and all the vertices. In this case, since we're just differentiating one, we basically just need the single point. And for each pair of the vertices and the face, we write on such form. Now, this is a prescription for this object. There's a factor entering from in the dialog. And what does this tell us? So to understand this thing, we can look at this picture again. So generically, the point sits outside of the plane. If we go to the situation by deforming this point, so that is now sits on the plane, then the projection becomes singular on the plane. We no longer have a generic polytope, but it brings it to a point. And by the property that I told you, that in this case, the latter part, this latter part just vanishes. And so this situation is exactly characterized by this factor, because this P dot n is just describes the volume of the simplices defined by this point and this polytope on the hyperplane. And when this vanishes, it just degenerates. That means that P has to sit on the hyperplane. So that tells us how we should think about the term entering in the dialog part. And this is quite general, because we can, apart from thinking about deforming the point, we can also think about deforming the line, or deforming the surface, and we'll try to understand what the result. And the factor entering the dialog is again related in this way. We can also do, in analogy, we can do this recursively. In the first step, again in this example, we project it onto a two-plane. But we can do further. Once we have this discontinuity, we can we have this differentiation. We can differentiate again, and in doing that, we are basically picking another point and do the projection, projecting on a line. And then on the other hand, we pick up a boundary of this triangle to be the new integration region. And also, once more, we can further project it down to a point. And this procedure actually gives us the information about the entire symbol entries that we need for the structure of this integral. So in the first step, the entry that we need is something describing the situation, characterizing the situation whether this point sits on the hyperplane. So in order to characterize it, we just need to pick up this point and also the three vertices of this triangle and write out the volume. And in the second step, we need something describing the distance between this point and this line. And in terms of the original geometry, what we need is exactly the 2 point defined in this line and 2 point defined in this line, and the volume computes the distance. And in the third step, for example, if we pick out this point to do the projection, then and take this point to be the integration region, then we need something characterize this distance. And this is nicely encoded in the volume of made of this vertices and this face. And so this basically gives us three combinations, invariant combinations made up of the vertices. And that's actually, when we lift up all of them in sequence, they actually give us one of the symbols entering in the whole symbols of the entire integral. And by enumerating all these such possible combinations, we actually get the entire symbols for this integral. And this is very general. it also tells us more, because when you look at this combination, there's a symmetry here. And the symmetry is this. If we start with some integral defined by this two polytopes, we can also think about switching their roles. Instead, we take this to be the integration region, but this to be our integrand. And then the symbol entry, due to the additive nature of this kind of object, for whatever integrals defined by whatever arbitrary polytopes, when we do this reverse, the symbol entry has to also completely reverse. And this actually give us, this fact actually give us an understanding of how the two pictures, one related to the discontinuity and another related to the differentiation, all these two pictures has to be related. So we start from the same picture, which we use to understand the differentiation. And in terms of the symbols, the information that it gives us is all the symbols apart from the last one. And the symbols in this part are associated to the geometry of the n prime and l prime restricted on this hyperplane. And when we switch it out, the structure we should expect is follows. After reversion, and here note that the rho of the n prime and l prime is also reversed. And in this picture, when we compute the discontinuity, we can basically use the same picture to understand the structure here. And so it's like this. Now here is our integrand, and to obtain the integrand associated to this one, we basically just need to restrict the original integrand on this hyperplane by computing its residue upon this. And on the other hand, given this picture, it appears that we have some integration region that is a kind of projection of the original one on this plane. This picture shows you there should be nothing happening because there is no intersection of this polytope with the hyperplane as we expected previously. But the configuration, we can analytically continue this continuation such that in some situation it has a non-trivial intersection. But actually this is exactly, this intersection is exactly the one that you may get from the point of view of doing projections through this point. And so there's really nothing different between these two geometric pictures. Okay, so this is a general story about this class of integrals defined by two pairs of a pair of two generic polytopes. Now, so far everything that I've described are about objects defined by linear boundaries. So the question is that is there some hope that we can use some of the observations here to deal with more complicated objects? And for this, for the rest of the talk, I'm just going to show you a very simple example, which is a four mass box. And previously, I actually intentionally used a very particular choice to make the situation more interesting, because here, when we vary the data, it's basically this u and v, we're changing the shape of the quadrant instead of changing the shape of the line. And the result is very well known, like this. So, depending on which kinematic region, suppose we are going to study the discontinuity of this integral. Depending on the specific kinematic region, the shape of the quadrant can change, and also, in particular, its intersection with the integration region could also change. And at the starting point, we are starting from the Euclidean region where we encounter no branch cut. And it is very nicely explained in this picture because there is just no non-trivial intersection between the integrand and the integral. Although here there seems to be an intersection, but the region is that of dimension 0. It actually doesn't matter. Now, the interesting thing is to look at what happens in such pictures, where we have an intersection, and the intersection is not a line. For example, if we look at the K1 channel, the particle 1 channel or particle 3 channel, we get the U to be positive but V negative, and the picture looks like this. So we can try our previous idea to restrict the integrand along the quadratic by computing the residue and do the integration over the non-trivial intersections. And it turns out that both we can compute it in either way we want, and the result correctly generates the expression we would get from the computing things, the discontinuity. Sometimes if we are not careful enough, we could, in principle, encounter more complicated situations like this. And this picture is basically about the picture associated to the same channel. But now the intersection has two irreducible parts. And it actually doesn't matter. As long as we follow the procedure and the sum of the contribution along these two intersections, we again recover the correct result. So this procedure should be something really general, and it's independent of how we do the analysis. To quickly summarize, here in this talk we are studying the class of integrals defined by a pair of generic polytopes. And we determine the analytic structure of these integrals and show how it's systematically encoded directly in the geometry. And we also obtain a geometric understanding of computing the discontinuities and also computing their derivatives with respect to the external data. And both of these are associated to certain projections of the geometry on a lower dimensional space. And we also show in the Formax box as an example to illustrate how some of the analysis here can be extended to more complicated integrals, and hopefully, perhaps in the near future, to some actual amplitudes, at least in some special series. And also note here that in the previous case when I computed this continuity, I'm not using anything directly extracted from the Feynman diagrams, and this computation is alternative to the Euro-Katowski rule that people use. And of course here we are just initiating the analysis of this geometric analysis on the singularity structure of physical amplitude, and there are many things remaining to be explored. Thank you.
Questions? With coffee break. Okay, if there are no questions, let's thank Ellis again. Please.